keynote speaker by Antonio Bermúdez.
Thank you. Thank you very much. I'm very sorry. So we were late, but it was not our fault, I guess. Yeah, my name is Antonio Mendez. So I will introduce myself. I come from Mexico. I'm a physicist. I work at Instituto de Física de Benemérita Universidad Autónoma de Puebla. And yeah, my interests are randometrics theory applications, disordered systems, nonlinear systems, and most recently also random networks. So what I want to present to you today are some recent results, which are indeed a continuation of a work we started some years ago with colleagues you already know, with Guilherme, with Jamir, Francisco, Rodriguez also. But maybe that's not the main point. I mean, I will not want to stress the attention on these new results, even though I think they are interesting. You will see in a moment, maybe. But I would like to stress a little bit the presentation on random matrix theory techniques, or the random matrix theory approach, because I believe, but this is my personal opinion, that random matrix theory is a good mathematical tool that we can use with many applications. In fact, for example, I believe, but this is again my personal opinion, that RMT is quite similar in a sense to nonlinear dynamics, in the sense that they are tools, mathematical tools that we can use to approach complex systems in general. And for example, while to apply nonlinear dynamics to a complex problem, let's say, one needs the problem to be described by a set of differential equations. That's the main ingredient. So for RMT to be applied to a complex system, one needs that complex system or process to be described by a matrix. That's the main ingredient, let's say. So then I will try to go fast on these RMT ideas, let's say, and then I will try to describe an application, a very concrete application. So I know that some of you are already very familiar with random matrix theory techniques, but for the ones who are not so familiar, so I hope this will be useful for you. Okay, so yeah, I will go to this. So I want to start with this slide, which is, I think, very important, at least for me. So this is the main let's say, philosophy behind RMT. However, it's the main philosophy from a physicist point of view. Now, what happened is that in the 50s, 50-something, so people was very interested in studying complex nuclei. And that problem is a problem of, it's a very complicated problem because it's a many-body problem. And then what people did was, instead of trying to approach it exactly, let's say, theoretically, so Eugene Wigner, introduced the idea of substituting Hamiltonians of very complicated systems by random matrices. That's the main idea. And the philosophy is written very clearly here. So the idea is the following. Look, what is required is a new kind of statistical mechanics in which we renounce exact knowledge not of the state of the system, but of the system itself. We picture a complex nucleus because, I mean, complex nucleus was the application in that time, but now we can substitute this word nucleus by system in general, right? We picture a complex nucleus as a black box in which a large number of particles are interacting according to unknown laws. The problem then is to define a mathematical precise way an ensemble of systems in which all possible laws of interaction are equally possible. So that's the main idea. So if we have a complex system, which can be represented by a matrix, which is very important, then we can replace that matrix that describes the particular system by an ensemble of matrices with the same properties of the original one, the same symmetries, and then by understanding the statistical properties of the ensemble of matrices, the ensemble of systems, one can make predictions or one can understand the average properties of the original system. That's the main idea. So it's a very powerful, let's say, tool, however, has its limitations because we are, in fact, forgetting about the original system and replacing it by a family of systems of the same kind, let's say. Okay, so indeed there are many applications of RMT. So it started as a pure mathematical tool here. It was introduced in physics in these applications, in nuclear physics. I, in fact, learned it in problems of quantum chaos and mesoscopic systems. And then most recently, we are applying it to network science, network problems. Now, it will be clear in a moment why RMT can be indeed applied directly to problems of networks, let's say. So just to finish with these RMT ideas, so it happens that RMT is known to describe universal properties of complex systems. I will show you in a moment in the example what we mean by universal. Also, RMT is associated with the limit of maximal chaos or disorder, let's say, complexity, maximal complexity. But what is important to know is that RMT does not distinguish between two systems with the same symmetries. So that's the main, let's say, drawback that we have to understand always, because otherwise we can make, let's say, wrong predictions. Okay, now, in the same way we apply RMT to Hamiltonians, which describe, let's say, quantum complex systems, which is the main, I mean, it's how it was introduced to physics, RMT. So now we are using, in the same way, RMT to describe, let's say, or to understand the properties of the adjacency matrices of complex networks. However, I put here adjacency matrices, but this, let's say, idea is not limited to adjacency matrices. Could be any let's say, matrix representation of a network that we can, let's say, use to which we can use random matrix theory to study it. And now, I mean, this diagram is just to tell you how we, let's say, approach the problem. However, this is, these RMT ideas are not limited to the, let's say, to quantum physics or to complex networks. And in fact, if you have any kind of system, could be of any type, could be pure mathematical system, could be a physical system, a chemical system, social system, whatever, and you can represent it somehow as a network, then you can indeed apply random matrix theory to it. But also not only systems, but also processes. For example, in physics, we have, let's say, scattering processes, which are represented by matrices. So if the process is complex enough, so we can substitute the scattering matrix by an ensemble of random matrices and try to understand, let's say, the process of scattering. No? So that's the main idea. So if you have a matrix, if the system or process which is represented by that matrix is complex enough, then you may use random matrix theory to understand something about it. Okay, now, in network science, we have lots of matrix representations of networks. In particular, we have maybe the most famous representation is the adjacency matrix, or the most used. However, we have Laplacian matrices, we have the form Laplacians, we have lots of representations. But we will use in particular adjacency matrices for this particular example. And we already know how an adjacency matrix is constructed. So if we have a graph, here we have a 5-node graph. So the adjacency matrix is a 5x5 matrix. So we put ones in the places where the nodes have connections. If the matrix is, if the network is non-directed, then we have a symmetric adjacency matrix. If we have direction in the links in the network, then we end up with a non-symmetric matrix. So, yes, please. No, no, we can go from any. Yes, yes, because that's the most interesting scenario. So if you have a complete network, then we have, let's say, a boring situation, a limiting situation. If you have, let's say, a network which is completely disconnected, then again, it's a situation which is not so interested. So the most interested scenario is in between, right? And then, for example, it's clear, we all know that the let's say, structure and properties of a network are reflected in the structure of the adjacency matrix. For example, if we have a very a random network, like a Neuros-Renyi network, so the corresponding adjacency matrix is a random matrix. Here we have a scale of gray because we have weighted adjacency matrices. However, for example, if the network is regular, the structure of the corresponding adjacency matrix is also regular. And if we have, for example, modular or hierarchical structures in the network and we label properly the nodes, then we end up with the structure also on the adjacency matrix. So what I want to say with this picture here is that if we understand the properties of the adjacency matrix, so we can maybe infer some properties of the corresponding network. That's the main idea. And this is, in fact, what we are going to use as a reference, let's say, the structure of the adjacency matrix. Now, we will go to the example, to the concrete example on how we apply, let's say, RMT to these kind of problems. And in particular, I'm choosing the multilayer network. We already yesterday saw a multilayer here, a social multilayer. This is also an example of a social multilayer. So we have individuals here, persons, which are connected among them, but also there are connections among the layers. So this is the general, let's say, construction of a multilayer. I will go to more details in a moment. But what's the main characteristic of this, let's say, multilayer construction? So the point is well, we will focus on two constructions. Let's say the multilayer, in which we have layers, in which we have nodes, which are interacting among them, and also we have connections between the nodes between layers. So this is called a multilayer. I mean, this construction, let's say, is called a construction the connection is in series, because if we want to, let's say, communicate one node of this first layer with one node in the third one, so we have to go through the middle layer. So the connections are in series. And what's interesting here is that if we construct the adjacency matrix of this complete multilayer, so we end up with a banded structure for the adjacency matrix. Look, we can have individual adjacency matrices corresponding to each of the layers that we call A here. This is not indeed a number, but it's a matrix. It's an adjacency matrix, the adjacency matrix of the first layer. The adjacency matrix of the second layer is here, the third one, and the M1. So in this construction here, we have a multi-layer of M layers. Now, since each layer is connected to the following one, we have also connection matrices between these adjacency matrices. And at the very end, when we connect all the adjacent layers, we end up with this structure, which is a banded structure. So we have all main elements different from zero within this band, and zeros outside it. So this is not then a traditional random matrix, because in random matrix theory we always or almost always have complete matrices. That's at least in the original ensembles and many of the new ones. So people used to work with full matrices, or even sparse matrices, but full, let's say, without any structure. Now we have here a problem in which we need now, let's say, an ensemble of random matrices if we want to approach this matrix, this realistic matrix, by a random matrix model, we need a random matrix model which has the characteristics of this particular matrix here, which is that we have a band, and we also have sparsity within the band. So that will be the main ingredients of our, let's say, a random matrix model, the one we will propose and use as a reference to this network problem here. So just to make it short, so we have a network model that may represent a realistic system. We represent it as a matrix. We identify the properties or the symmetries or the structure of the matrix, the adjacency matrix, and then to try to understand the properties of this matrix, we create a random matrix ensemble. That's a process. Then we will study the statistical properties of the random matrix ensemble, and with this we will try to make predictions about the properties, the general properties, statistical properties of this matrix here. And then with that, apparently, we will understand something about the network here. That's the idea. Again, also, sorry, we will consider this another construction, which is a multiplex, in which each of the layers, which are represented by these adjacency matrices here in the main diagonal, are all connected all to all. So we have a main, let's say, band of the adjacency matrix, the total adjacency matrix is here, but we have identity matrices in all the matrix here. However, this matrix is very sparse because these are identity matrices, and we have lots of zeros outside the band and inside the band if the connections are not so many here. Okay, so we have these two constructions that we are interested, and then we will look, let's say, for a reference model, for a random matrix model that we will use as a reference to study these two matrix setups. So, fortunately, we have a model which is called the band random matrix model, which was proposed in the 90s by some colleagues who are physicists, and this random matrix model was inspired by two, in fact, physical systems. It's a model, let's say, for quantized chaotic systems. So it happens that the Hamiltonians of quantized chaotic systems have a banded structure. So it was a model for this family of systems, but also for quasi-1 disordered wires. So it happens that in some bases, the Hamiltonians of quasi-1 disordered wires are also banded random matrices. Banded matrices which can be seen as random. So that's why these colleagues here propose this random matrix model. Now, this is, I think, the most important slide of the presentation because all the information is here. And this is the main result of this paper here that I will try to go slowly. I mean, just to, in the next steps, the things I will do will be clear. So, these colleagues defined the Hermitian banded random matrix model. They didn't call it Hermitian, so I'm calling here Hermitian because we will use later a non-Hermitian model. But so I will put here the Hermitian banded random matrix model, and it's defined as a set of real symmetric matrices whose entries are Gaussian random numbers inside a main band at the middle of the matrix. And that's it. So this model has two parameters, which are the size of the matrix. Let's say, so we have this construction here. Let's call it A, the matrix. So all the elements inside this band are different from zero. We have zeros here, and the parameters of the model are the size of the matrix and also the bandwidth, which is this here. So that's the two parameters there. Now, what happens is that one may believe that if one moves these two parameters, B and N, in an independent form, right? I mean, fixing one and moving the other, so one can have different situations. I mean, that's correct. However, one of the main, let's say, ideas behind random matrix theory is to try to find a universal parameter. That means a parameter, a single parameter, which is a function of the parameters of the model for which the properties are fixed. That's the main idea. And this is what is done here. What the colleagues did was to look at this quantity, which is beta. I will use this beta throughout, all the way in the presentation, which is what we call the scale localization length of the eigenfunctions of a matrix. So the idea is that having a matrix, we diagonalize it, we compute the eigenvalues and eigenvectors, but from the eigenvectors, we compute the entropies of the eigenvectors. So this is a measure of the extension of an eigenvector. So if the eigenvector, for example, corresponds to a diagonal matrix, the eigenvector will have only one single component, and the entropy will be 0. So this is a situation of minimal information, let's say. While, for example, if we have a random matrix and we diagonalize it, full random matrix, and we diagonalize it, so the eigenvectors will be complete random vectors. And the corresponding entropy will be maximal, and will be proportional to the size of the matrix. So we have these two limits, the integrable limit and the full, let's say, chaotic limit, or the disordered limit and the non-disordered one. So depending on the problem, so may have different interpretations. However, this quantity gives you the spreading, let's say, of a wave function on a given basis. So if we compute the average, yeah? Yes, please. Yeah. Yes. A full random matrix, the full random. Yes. Yes, please. Yes. Yes. Of Wigner, yes. Yes, Wigner. Yes. Uh, look, yeah. The GOE is the ensemble of matrices. So the Gaussian orthogonal ensemble is defined as a set of matrices of large size, which are full of Gaussian random numbers with mean 0 and variance 1. So if you have that matrix, which is the GOE, and you diagonalize it, you can get eigenvalues and eigenvectors. So whatever quantity which you can measure from eigenvalues and eigenvectors, whatever the statistics you would like to compute, is a GOE statistics. And yeah, for example, you can work with the spectrum, yeah, and then you can, for example, compute the distribution of mean level spacings of distances between consecutive spaces, and this is the P of S of Wigner, but this is the GOE limit for the spectrum, let's say, and for that particular quantity. Here, for example, we are looking at the eigenvectors, and so if we compute the entropies of the eigenvectors for the GOE, then we call it the GOE limit also. Yeah. Yes, please. Yes. Oh yeah, it's the same. It's the same. Yeah. Thank you very much. I messed it up. Oh, yeah. This is n. Is n. Yeah, this quantity has to be the sum over one vector, let's say. One vector. Yeah, but for example, in practice, when we diagonalize a matrix, so we compute the entropies of all the vectors, and we compute then the average of all the vectors, yes. And we compare that average with the average, let's say, of the GOE, or the corresponding ensemble, because this GOE is an ensemble of real symmetric matrices. But later I will use non-symmetric matrices, though, so I have to use the corresponding ensemble as a reference. Thank you very much. And yes, this has to be n. So what these colleagues found here is that this quantity, which is the scale localized length, I mean the average measure of the extension of the eigenstates for this model, for the model of banded matrices, scales as this parameter here. This is the scaling parameter. So this is a combination of the two original parameters of the model, the band size and the size, the bandwidth and the size, in a kind of non-so-trivial way. And what happens is that if one plots this quantity beta as a function of x, which is now the universal parameter, no matter which combination of these two things we put, all points fall on one single universal curve. And that's, let's say, the main idea behind random matrix theory. And why this function is this curve is important? It's important because it says that I don't need, in fact, to move independently the two parameters of the model, but the ratio is important. This ratio is important, b squared over n. If I fix this ratio here, so the properties of the system will be exactly the same, no matter the combination. So, and this is very important for design also, because, for example, if you recall, this band random matrix model was also a model to describe disordered wires. And for this particular application, for disordered wires, these two parameters have physical meaning. For example, B is the width of the wire, and L is the length of the wire. And then, for example, if you, and also, the parameter beta for this problem of disordered wires has also physical meaning, because it drives the wire, let's say, from conducting to insulating, or vice versa. So small values of beta, which are here, are proper of an insulating wire, while the large values of beta are proper of a metallic wire. So, for example, if we have an experiment and we know these two quantities, for example, in the lab, so we can make a prediction about, let's say, the average behavior of the system. And if we want to design something or modify it to, let's say, make it more conductive or less conductive, so we can, in fact, try to play not with one single parameter, but with a combination of both. So we have many ways to play with this parameter to move the system upwards or downwards. Yes? Here, gamma is a numerical constant found here, which is of the order 1. So it's just yeah. No, it's a constant that depends on 1. Now, at the moment, these guys, these colleagues made this paper, so they proposed this scaling function just phenomenologically, numerically. But then, as it was, let's say, interesting, so lots of other colleagues came to the game. And in red, for example, there are so many some papers which approach this problem theoretically, and they prove that this has to be correct. I mean, it is correct. So we will take these results, these ideas as a reference, and we will construct a new, let's say, a random matrix model for our particular problem at hand. Now, we also, so I have to, I said at the beginning that this is a continuation of a work we made some years ago with Guilherme, Francisco Rodriguez, and Jamir, in which we work on the Hermitian diluted banded random matrix, because so this model here is just a full banded random matrix model. So we came out with the diluted version of it. We include an additional parameter. in particular to apply it to multi-layer random networks as the ones I presented here. So the difference between these results and the ones I will present today now is that we are now trying to approach directed networks, which means that we were dealing with non-Hermitian matrices. And these two works here were for Hermitian matrices. So what we found in these two works is that the scaling is almost the same as the previous one. However, it's a bit modified by an exponent here, which is of the order of 1, by the way. So this scaling then is kind of universal, and then we will try to use all this information to try to first propose a random matrix model, and then to scale the directed multi-layer networks I presented at the beginning. So the non-Hermitian diluted banded random matrix model is defined here. Is very similar to this matrix here. So we will have a matrix which is banded, has 0 here. However, it has also zeros here inside. So we have now then 3 parameters. We have the matrix size n, the width b, and alpha, which characterizes the sparsity of the band, of the elements inside the band. So this parameter alpha goes from 0 to 1. When it is 0, we have nothing in the band. We have a diagonal matrix only. And when alpha equals 1, it reproduces a full, let's say, banded random matrix, but non-Hermitian, which is important here. So we have then 3 parameters, and we will try to find the universal parameter, as in the previous works, which scales the properties, the spectral properties of the model. That's the main goal. Now, here we will use, instead of the GOE, because now we are not dealing with symmetric matrices, we will use the Genebre ensemble, which is, specifically the real Genebre ensemble, which is an ensemble of Gaussian random matrices which are non-symmetric. That's the definition. Okay, so what we do to find the scaling function, the scaling parameter of this model? First, so again, we compute the scale localization length for the eigenfunctions of this model. We use the real Genebre ensemble as a reference, and we plot this quantity as a function of this new parameter x that we are proposing now. I mean, it's just a trial let's say, function, which depends on the ratio b effective square over n. So n is the size, and b effective is this product here, this alpha times the bandwidth. This we call it effective band because it's the average number of non-zero matrix elements per row, let's say, in the matrix here. So if we do that, so we have beta as a function of x here, as before, as in the paper by our Russian colleagues. So we have this kind of curves, quite similar. However, they are affected by the sparsity inside the band, which is expected. I mean, that the sparsity has to have a strong, let's say, effect. And then, so our main idea now is to try to collapse, let's say, all these curves by finding a new parameter x that can incorporate this effect of alpha. That's the idea. Yes. Yes. Here we have lots of each point is a different combination of n and b, and alpha is changing in this direction here. So we have hundreds of combinations here. But what is important is that for a fixed alpha, so we have a single, let's say, universal curve in the sense of fixed alpha. Okay, now. Let's note that the scaling that we already saw for the Hermitian diluted banded random matrix, which is this one, is equivalent to this function here. And this is very important and very useful, because we plot now, instead of beta versus x, this ratio versus x in a log-log plot, then we have a straight line, right? So this is the same data here, is here. And in fact, so we observe that these quantities have a straight form, at least in a quite large range of parameters. I will show you what is large in a moment. But if we perform linear fittings, so we realize that these are not just straight lines with slope 1, but they have a slightly different slope, which depends on alpha. And the slope is this, it's here. It's close to 1, but it's not 1. So then we propose this new scaling, right? We propose this ratio here to go as x asterisk, which is this quantity here, where this gamma and delta depends on both on alpha. So if we plot now then this ratio as a function of x asterisk, so we expect all these curves to fall one on top of the other. And this is what we observe here. So this is already a scaling, right? So we are collapsing all the curves here on this single one, at least in a wide range of parameters, in this particular range here. And for alpha larger than 0.4, which is all the data we have here, so this scaling works quite good, right? So if we go to the original representation, which is beta now as a function of the universal parameter, so we have the collapse of all the curves, and we claim that we already found the universal scaling parameter, which is this one, that now depends on the 3 parameters of the system, of the random matrix model, but also we have a scaling function for this quantity beta here. Now, this is already good, let's say, because we already have the scaling of the non-Hermitian diluted banded random matrix model. But now we will use this as a reference to scale the adjacency matrices of the multiplex setup, of the multiplex network, which are not exactly the same as this. Okay, so sorry? Delta and gamma are still of the order of 1. So delta is here. Is between 1 and 1.2, let's say. Yeah. Okay, so let's go to the directed multilayer network. So we have, just to recall, because I presented already this adjacency matrix before. So we have the adjacency matrices of the layers in the main diagonal, and also these connection matrices here. So we define this ensemble as so we have again 3 parameters: the total size, the size of the number of the layers, the size of the layers that we consider here to be equal, and also the sparsity of the adjacency matrices of the layers. And now, since this is the directed multilayer, so this matrix is non-Hermitian. That's the main idea. Again, so we do the same procedure as before. We redefine the B effective as, again, the number of non-zero elements per matrix row in average number of matrix elements per matrix row in the adjacency matrix. So we plot this beta as a function of x. We see the same effect as a function of alpha here. And we perform the same kind of scaling for this model here. So doing exactly the same, we end up with a good scaling, very good scaling, where now the scaling function is the same, but the scaling parameter now depends on the particular parameters of the multilayer model. So we have the size of the layers, the number of layers, and the sparsity of the layers. So this is very important again, because so we can design, let's say, the properties of a multilayer network. So, for example, if we have a multilayer network which has, for example, a value of x asterisk around here, let's say, with a let's say beta of 0.5, and we want to make it, let's say, more conductive of information of whatever, no? So we can move this curve. We can try to push this beta to this part of the curve by moving this parameter here, but we can do it by moving the 3 parameters at the same. I mean, by many different combinations, not only one. I mean, one can, for example, believe that by let's say reducing the number of layers, one can make this matrix, this network less more conductive, and that's true. But also we can move this other parameter. So this may be used also for designing. And then so we can also try this other setup, which is the multiplex directed networks, which again these adjacency matrices here are non-symmetrical. And then we have the identity matrices outside. We redefine again the effective band as the size of this as the band within these adjacency matrices, and then came out with the same kind of scaling. Again, we find a scaling parameter. So conclusions. So we showed that in particular the normalized localization length of the eigenfunctions of the non-Hermitian diluted band random matrix model and also of directed multilayers and directed multiplex networks scales as this quantity here, where we can define, right, the scaling parameter as this quantity here, where this B effective depends on the particular model we are trying to describe. Now, what happens is that this X asterisk here, this scaling parameter, also scales all other properties, spectral properties of the model, but I'm not showing it here. So the importance of this, let's say, analysis is that it does not apply only for one quantity. It applies for all other, let's say, spectral quantities, but also dynamical quantities and also. So this parameter then scales all properties of the model, in fact. Also, it's interesting that this scaling can be written in this form that I think I don't have much time to explain, but it's interesting because it differentiates the contributions of the let's say parameters of the system in the behavior of the complete system. And as I said, so this scaling can be used as a tool to predict the localization properties of eigenfunctions of, let's say, directed multilayers and directed multiplex, which may have implications in the dynamical processes which are on top of them. That's the main idea. But again, what I didn't put in the conclusions and what is important, I think, to stress is that these kind of ideas of modeling, let's say, systems using random matrix theory and using scaling analysis, you know, to look for universal properties of a family of systems are not restricted, let's say, to network systems, which, I mean, are very simply approached because they can be described by matrices. However, if you have any system or any process that could have a matrix representation and the system or the process is complex enough, then you can use RMT tools to characterize or try to understand the system. That's the main idea, and that's it. Thank you very much.
Thanks, Antonio, for your nice talk. We have time for some questions. Anyone?
So very nice talk. Thank you.
Thank you. Thank you very much.
So have you tried to look at the level spacing?
Yes.
How do they look like?
Look, for this now, right now in the let's say random matrix theory community, the level spacing distribution is not so fancy anymore. Mm-hmm. First, because it has been understood or shown that it's not so sensitive to let's say, it's not so sensitive. indeed, for a wide range of parameters, it gives predictions for systems which are very far from the Gaussian ensembles, as if they already had the properties of the Gaussian ensembles, as if they were completely chaotic, and they are not. So people use other quantities now, like eigenvector properties. However, concerning the level spacing distribution, for these matrices which are non-symmetric, which are non-Hermitian, and now there are new quantities which are computed instead of the level spacing distribution, because these eigenvalues now fall on the complex plane. And what people use is to compute the ratio between nearest distances in the complex plane of the eigenvalues. And yes, we compute them. We compute the average and the statistics and the distributions. Well, are not very interesting, yeah. But they scale with the parameter x asterisk, which is very important.
Yeah. No, I forgot that the eigenenergies are not going to be real anymore.
Yes, they are complex. Yeah.
Right. Yeah, thank you.
We have more questions?
Okay. Yes.
Hi. When you were explaining about the, I think, multiplex agency matrices,
yes,
you said that the off-diagonal entries, you would have like identity matrices.
Yeah, in the multiplex construction, yes.
But I don't really understand why you would have like identities in like each one of the entries.
Yes, because we want in this scenario, as he already presented yesterday. So we consider that each layer is composed by the same agents. Let's say if it is a social network, are the same persons in each layer, and each layer is a different how to say it? Community setting. Exactly. However, since they are the same persons in each layer, so they are identified with each other throughout the complete network. So that's why we put identity matrices to connect the layers. I mean, to connect the same individuals.
Thank you.
That's the idea.
More questions?
Antonio, just
yes.
out of curiosity, do you know how this scaling would be different if the elements of your matrix are correlated? Do you think it would be
that's a good question.
The functional form will be similar to this one, or?
That's a good question. I don't know.
Okay.
I don't know. No idea. Never thought about it.
Okay.
Yeah. Thank you.
Excuse me, I have a question.
Yes.
Sorry, I missed here. What was the importance of being directed multilayers or multiplexes?
Well, in
I
fact,
mean, except for being more sparse.
No, it's not related to with the sparsity. No, in fact, directed networks are a bit more appear more in nature indeed than non-directed networks. For example, if we already saw talks the first day about the power grid, for example, and this is a directed network. So the flux is in one direction only. And for example, transportation networks, communication networks, even social networks are directed. So that's the motivation. And in particular in the multiplex setup, so there are many examples of directed constructions. Yeah.
What I mean is, will the theory that you develop depend strongly on being directed?
Again, sorry?
I mean, will all the theory that you have developed here, are they strongly dependent on being directed layers?
No. In fact, we found very similar parameters and very similar scalings as in the case of non-directed networks. But this is because, well, this is a random matrix model. And a random matrix model has this let's say, problem that it sometimes washes out important, let's say, physical effects. Yeah. Hi. Sorry. Yeah. Yeah. No, right. Sure. We didn't try that situation. No, this is a first, let's say, attempt, let's say, to directed multiplex. But there are many parameters, of course, that can be included. Yes. Yeah. We didn't look at it.
Hi, thank you.
Yes.
So why do you need the alpha? Because indeed the band is already asymmetric. Because
yes.
You take, so maybe you are more interested in reciprocity than asymmetry.
Well, alpha here is a parameter that quantifies sparsity, which is an ingredient of networks, let's say.
Yes, but is independent from being directed or not?
Yes, it is.
So your band is already directed in principle because it's asymmetric.
Yeah.
Okay, so you want to add an extra term, this is the sparsity, not just the directness.
Not really wanted, but needed, because the model, the original model, is a multiplex network, which is by definition a sparse matrix. So I need it. Okay. I need the parameter alpha.
We have time for more questions. Okay, let's thank the speaker again.
Thank you very much.
We now have a coffee break. We will return in about 30 minutes. It's the coffee break now.